Okay, welcome to this section on metaprogramming in Julia. This is a pretty cool topic, I think, because it's about do something quite esoteric, which is manipulating or changing your Julia code at runtime, which is a very powerful ability that allows you to do a lot of things that you can't do in a lot of programming languages, especially avoiding boilerplate code. So the topics we're going to look at first we're going to look at program representation, and that's in this video. And that's important to understand. If you're going to manipulate code, you have to understand how is actually code represented in Julia, what kind of objects are involved. And macros, which are facilities for actually doing the manipulation of the code. And as well as we're going to look at actually creating code from scratch at runtime. So let's start with looking at the representation of programs. To understand that, we have to first look at how parsing works in Julia, how we take some textual representation of a program and turn that into some kind of representation of that code in memory that Julia can work with. And we're going to look at something called quoting, which is a way which we can avoid having some code getting evaluated right away or running right away. That's important if you actually want to be able to do something with the code before it runs. And evaluation, which is taking some kind of frozen code that hasn't been evaluated and running that, as well as expressions and symbols, which are kind of the building blocks of a Julia program. But let's first look at parsing. You've probably seen me in a previous video use parse to take some string representing a number and turning that into a Julia integer or floating point number. If we do this with an expression like this, you might think, well, this is going to give us a 7, but in fact it's going to give us the code representation in memory for this in Julia. So this colon and parentheses is how Julia is visualizing that we're getting actually an expression object out from this. We can evaluate this expression, and that's when we're going to get 7. And we don't have to parse a string. We can actually just write this directly ourselves by putting a semicolon in. Doing it like this is what's called quoting. So that allows us to defer the evaluation of this snippet of code to later, so we can actually try to do something with it in the meantime. So just to show you that this is what's going on when you're reading a Julia program, we're going to define some snippets of code in two files, point.agl defining a point object and a function operating on points. So this is it's not important exactly what this does, is I'm just using some examples from previously. So let's start by reading the point file, and you can see we get this definition of a point in a string representation, and then when we parse that, we get the quoted code that hasn't been evaluated yet, because if we're trying to actually create a point object, we're going to get an error message. Julia doesn't know the existence of any kind of point type in its image or environment. So we have to actually evaluate this expression, and that is what is going to allow us to create point objects. Now we're going to go further and we're going to load the function. So we're going to have some points to test with the function p and q. So with read string, I'm reading the function definition, parsing it, and you can see that again, if we're trying to do a comparison here, we're going to get an error because this has not actually been brought into the Julia environment yet. We're just having a dead chunk of code. But we can evaluate this, but we're not quite done, because when we're doing this, we're going to see that we get an error message. And that's because Julia is trying to prevent you from accidentally adding a method to a function without your intention. So we have to import less than from base. So we're explicit about Julia that we actually want to add a method. Now we can evaluate it, and here you can see that P less than Q actually works. So expressions in Julia are everywhere. Everything is an expression. A Julia program is really just a large tree nested expressions. So let's just look at these expression objects. We're going to just put some values and some variables. I'm just going to show you. So this is a regular expression, right? Multiplying and adding some values. Now we can sort of freeze dry this by quoting it and putting it into a variable. And if we look at, well, what's the type of that? Well, that's an exper object. So that's an expression object. So a Julia program is really made up of a lot of these, and we can inspect what actually contains an expression object with field names. It says it has 3 fields: head, arguments, and type. I'm not going to cover what type contains today. It's not that important. The head says sort of the main category, whether this is a function call or an assignment or a type definition. So add is a form of a function call. And with arguments, you can see that plus it's adding up these 2 sub-expressions. We can fetch out this individual part. It's just a regular array, so I'm using index 2 to get the second part here. We have this practical function called dump, which allows us to show the whole expression tree. And this contains a lot of information. It tells us what are the types of the individual parts, as well as the values contained. Could be a little bit hard to read, especially if it gets larger. So I quite prefer this meta.show s expression, which is an alternative way of showing these expression objects. So just to show it more clearly what this does. So we have this expression here, and we're using our meta show s expression. We get this, and we just clean this up a little bit. We get this, which if you ever looked at Lisp before, this should look quite familiar. It looks kind of like a Lisp program, and that's a little bit of the cool thing about Julia, I think, is that right underneath the surface, it's a very similar to Lisp, and in fact, the parsing of Julia actually is done in a dialect of Lisp. So this could be represented graphically like this. We're having an expression object at the top, which is a call of type plus, and it's taken 2 arguments. The leftmost here where we're multiplying an x with the 3, and the right one where we're multiplying 2 with a sub-expression which is 4 plus y. I color-coded this, so green is all sorts of operations, yellow are variables, and red are literals. So you notice that there's all these columns in front, and these are in fact symbols. You can see that if we dump x, it says that in front of the plus it says symbol, and if we just access that directly with the square brackets, you can see that it has this colon plus. And if we take the type of that, you can see that that's a symbol. We can create and use symbols easily. Just put a colon in front of the symbol name. We can use a symbol construction with a string. Now, symbols are quite similar to strings, but usually they are just one element. So if I create this symbol of the same name twice, it's going to point to the same object. At least in most programming languages, there's going to be a hash lookup and find if the symbol already exists, so we can point to the same one. That means that in a lot of languages it would typically be very fast to compare 2 symbols because it's just a pointer comparison. So often we see them used in dictionaries as keys for looking at values. So here I'm creating a dictionary with symbols, and we can access the element at the key 4. So we're not going to really look much further at the program representation. We're going to get a little bit more into this as we're looking at macros and creating code on the fly. But let's just summarize what we're going through. A Julia program is a tree of expression objects, and what's neat is that we can actually inspect this expression tree in Julia itself, because the expressions are regular Julia objects. We have the same facilities available to parse and validate Julia code available to us at the REPL as those used by Julia, and that's not given for all programming languages. So this is kind of a bit of a unique feature for Julia.